All right, the last part of this chapter is the deviation from ideal behavior. So when we look at we look at real gases. This is what the molar volume should be of the ideal gas, and you'll notice that it may be close. In some cases, it's very close. It hits it exactly close, close. Some cases, it's really far off. The question is what's going on? So if we were to graph, this is R, so the gas constant, which you'll graph when you do your gas stoichiometry, versus pressure. For an ideal gas, this is what you should see. Notice that we behave ideally to about 1 atmosphere, and then after that, we definitely go off the rails. So the question is what are these gases doing that makes them deviate from ideal behavior? Okay. Here's another variation. You can look at it. This breaks it up. This is the exact same gas. The previous was different gases at the same temperature. These are different temperatures of the same gas. And again, ideally they should behave here. And if you'll notice that they're really behaving the best at high temperatures. So what's going on? Well, they deviate from ideal behavior. Gas molecules occupy a small fraction of the total volume, remember? This is at low pressures. But here's what happens at high pressures. You've got a much smaller volume and you have more particles. Think of it this way. If you have a big box and you're packing bowling balls in it, okay? If you have a refrigerator box, you can pack so many bowling balls in it, right? Now, can you pack a bowling ball in a little jewelry box? No. Because when you have huge volumes, you can run the bowling ball all over the place and it's no big deal. Big room, roll bowling balls, you're fine. But if you're in a really tiny room and you've got bowling balls, then you have a major problem. So what we're basically saying here is at high pressure, you have low volume. And with low volume, then the atoms start to create havoc. Because we made two assumptions. First off, we said that gas particles have negligible volumes. Negligible means very small and can be ignored. Well, that's not the case at high pressures, because at high pressures, you're basically trying to pack bowling balls into small spaces. Okay, the other thing we said was that there was no attraction between particles. Have you ever played that game where you have like the tennis balls and the Velcro pad and you throw the ball at it and it sticks? Well, that's attraction, okay? So if you have like just straight ping pong balls, they might bounce off each other, but if you coated the ping pong balls in like a little jelly or honey, yeah, I know that's gross, but think about it that way, then when they impact, they would stick. So what happens is van der Waals was studying these and studying intermolecular forces, and what he came up with was the van der Waals equation. You will not be asked to use this, but you will be asked what's going on. And so this one is, this is the volume. This corrects for actual particle volume. Okay, in the pressure, that it counts for the attractions. So what van der Waals equation does is, remember, the ideal is PV equals nRT. It's the same thing, except this is correct. Pressure is being corrected for attraction, and volume is being corrected for actual particle. So here, where do you get these values? You get them off of tables. Again, you're not going to be asked. A corrects for the attraction of real gases. B corrects for the volume. And we're done with this chapter. But the take-home message, I've gone back here. The two things that you need to know about the van der Waals equation is it corrects for actual particle volume and attractions between the two particles. That's the important of van der Waals equation because it accounts for real gases not behaving ideally. Okay?